molecules will desorption. And if you keep to that, at one point, the molecules will be all lying down and cover the whole surface of graphene. Of course, if you keep increase the temperature, all the molecules will be disappear. Let's see what we observed. Before we see the Raman spectrum, I want to talk about the UV visual spectral characterization we use to measure the orientation change of these molecules. So this molecule has two particle absorption peaks, here Q1 and Q2. These two peaks contributed to the aggregated or individual molecules. So if we can get the ratio of these two peaks, then we can know which configuration is dormitory. So here on graphene, we see the Q2 peak is actually increased with the annealing temperature, but without graphene, it decreased, because in this system, what will happen is only the decrease of the number of molecules. But in this system, the molecules will change from upstanding and lying down, and then we have more confusion to this peak. So more interesting is that we know sometimes the Raman signal is proportional to the absorption intensity. Here we see if we use 633 excitation wavelengths, the absorption is lower, the red line. The absorption is decreased. But what we found is that the Raman intensity actually increased. Like we show here. Like what we show here. So with graphene, if you increase the temperature, the intensity increased and then decreased. And for the system without graphene, the Raman signal keeps decreasing. Yeah, here is another peak. So in this process, we can imagine what happened. Like for the first step, all the molecules are upstanding, and the number of molecules is n, and the Raman intensity is I. And if we anneal it on a lower temperature, the molecule will become abundant. But the number of molecules will keep at n, but the Raman intensity actually increase. And if we keep doing that, all of the molecules will lie down and cover the whole surface of graphene. Then we lose some of the molecules, but actually the intensity gets stronger. If you keep doing that, the molecules decrease because of the desorption, and the Raman intensity will decrease again. So if we compare these two states, like we know how the intensity change, we know how the number of the molecule change, then we can calculate the enhancement factor purely for CM, for chemical mechanism. Like what the result we get here is for different vibration mode, the enhancement factor is very different from 1 to 43. Yeah. So in this part, we see that GERS is a molecule orientation sensitive, and it offers a very good stage to study the molecule orientation dependence of CM, which is but this is a challenge in conventional cell system, but it's very easy to achieve in the cell system, in the GERS system. So before we didn't mention the molecules, but the molecule we actually test lots of different kinds of molecules, and some of them has a GERS effect, some of them doesn't have, some of them don't have. So we are wondering, like, what kind of molecules can be enhanced? Here are all the molecules we did. Most of the molecules, not all. Yeah. So what we found is there are two properties from the molecules can affect the GERS effect. One is the molecular homoluminal energy level, and another one is the molecular structure. So here we choose molecules, they have the similar structure but different home and LUMO level, and then another class molecules, they have the similar home LUMO level, but they have different structures, symmetry. So these two factors both of them can contribute to the molecular graphene interaction strength and affect the enhancement factor of GERS. For the first group of molecules, we see these molecules, they are very similar and they are all planar. They can contact with graphene very well, but the Raman enhancement effect is very different from graphene. Like for the COPC, the signal is much stronger than the F16 COPC. So that means this effect is very related with the molecular home and LUMO energy level. And if we look at the vibration mode, different vibration mode, the enhancement factor will increase with the frequency of the vibration mode. We developed a map model to explain it. So the model tells us if the home and LUMO fit these four conditions, then we can get stronger Raman enhancement. So the model and the experiment fit with each other very well. And for the second group, the energy level are very similar, but the molecule has very different symmetry or molecular structures. So we also did the calculation. We found for those molecules, like the distance between the molecule and graphene is very different. So as we mentioned before, chemical mechanism is strongly related with the distance. So yeah, that's why they have very different enhancements. If we conclude all of the molecules, we found those molecules which has planar structure and has very high symmetry, like CD4H, B4H, B2H, and has very good energy level match with the graphene level, then they will have very strong Raman enhancement. So this was supported by UV visible absorption. UV visible absorption is very powerful. Like in our study, like we can tell, like the molecules with stronger GERS effect, normally the absorption structure change a lot after deposit on graphene. But for the molecules with smaller, with weaker GERS effect, the absorption peak doesn't change too much or doesn't change. Yeah. So in this study, we know like GERS has strong molecular selectivity. So that means it has very high selectivity. Yeah, it can be very promising in some applications for the molecules. So next, I will talk about the graphene, the factors from graphene side, like the graphene thickness. What we found is not only monolayer graphene, but pure layer graphene also have significant enhancement factor. But for multi-layer graphene, the GERS enhancement intensity actually decrease with the increase of the number of layers of graphene. So this is because the absorption of the graphene layers and it decrease the interference effect from the substrate. But for like here we measure 1 to 6, they're almost the same. We also studied the graphene flaming level, the factor to the GERS effect. We apply an electric field to the graphene, and we can change the flame level of graphene. And what we found is the intensity change, the intensity of the molecular Raman signal change with the applied electric field. Also, graphene is only one kind of 2D materials. It has lots of similar 2D materials. And so what we found is not, of course, not only exfoliated graphene, CVD graphene, graphene oxide, or graphene content dots, or some other graphene derivatives, all of them have the similar effect. But we found for some other 2D materials, they are all flat, they are all non-metal, but we see more or less they have the enhancement effect. Of course, regarding to the enhancement factor, graphene is the best one. So at the very beginning, we are very surprised that HBN also shows the enhancement effect because it's an insulator. And it won't have very strong interaction, the charge transfer interaction with the molecules, but we see it has very significant enhancement. So finally, by the assistance of UV absorption spectroscopy, we think the graphene and HBN follows the different mechanism. Like for HBN, the bond and nitrogen bond is polar. So you can have very strong dipole-dipole interaction with the molecule. But for graphene, it's charge transfer interaction. So both of them can enhance the second step, but just based on different mechanisms. Actually, one of the advantages for HBN is that it doesn't have very strong thickness dependence. Even for very thick HBN, the enhancement can be very strong, or even stronger than the monomer. So that means we have more flexibility on choosing the substrate. So on this part, so what I want to tell is this effect is not only limited on monomer graphene, it can apply to the other graphene and to the other graphene derivatives. So it's very flexible on the material chosen, and that it also offers a good stage for us deep study the chemical mechanisms, because all of these materials, all of these derivatives support the CM mechanism. So next, I will move to the laser part. So I will just introduce it very briefly. So why do we? So for the laser wavelength dependence, the motivation we do this is because we want to know if the ground state charge transfer or excited charge transfer, excited state charge transfer for this system, for the chemical enhancement in GERS. Like in the ground state charge transfer, the maximum enhancement will happen. Okay. So here I think it's I did something wrong. They should be changed the position. So the maximum enhancement will happen at the molecular electron transition resonance. But for the excited state charge transfer, the maximum intensity will happen at the charge transfer state resonance, because in this mechanism we think there is some neo state generated between the HOMO and LUMO. So the enhancement will happen here. And here is the principle telling us why the Raman intensity has the laser wave dependence. So from here we can see if the laser energy is equal to the electron transition energy, or is equal to the transition energy minus plus the phonon energy plus or minus, then you can get the incident light resonance or scattered light resonance. And depends on the phonon energy. For the scattered light, for the scattered resonance condition, you will need smaller or higher excitation energy. Here is the results we got. So those are for different vibration modes, and the Raman intensity change with the excitation wavelength, excitation energy. What we found is it follows the molecules electron transition state very well. We didn't find any charge transfer state here. What we can clearly see, this case follows the principle we introduced before. So we think is the evidence to tell the GERS is the ground state charge transfer mechanism. Here is just the data we extract from the vision. So about the laser polarization, so we want to do this is because for some of the molecules, it has very high photoluminescence, and it's very hard to get the Raman signal on the silicon oxide on the substrate without graphene. But we want to compare the Raman intensity with graphene and without graphene, so we can tell the enhancement factor. So here we developed a method it's called the polarization difference technique. If we insert halfway plane and analyzer into the optical path, then we can get the depolarization ratio of the system, and finally we can get the Raman signal of the system with graphene and without graphene. And here clearly show that for the rhodamine 6 molecules, the peak at around 600, the intensity of graphene is stronger than that without graphene. Yeah, that's the advantage of this technique for studying the high frequency continuous molecules. Okay, here is a slide showing on graphene, the molecules are more stable on the area without graphene because you see the decay of the intensity is lower than the system without graphene. So it's actually much strong, much stable on graphene. And you can use stronger laser power to detect it, and don't worry about the damage of the molecules. So for the laser part, we use the wavelength dependence to tell like the mechanism is ground state charge transfer mechanism, and we developed the polarization difference technique for the high photoluminescence continuous molecules. So in the end, I will spend like 5 minutes to talk about the GERS. As I mentioned before, GERS has lots of advantages, including the uniform, stable, and repeatable, and low noise, and quantitative Raman signal. And it has very high selectivity, sensitivity, and also the molecules can be controlled the distance, the orientation, and in the system is a purely chemical dominated system, so we can study the chemical mechanism very well. But one of the disadvantages is the enhancement factor is relatively low. So for many practical applications, we really want the high enhancement factor. So here, what we do is we combine the conventional SERS system with the graphene. We separate the metal and the molecules with graphene. So because graphene is very thin, the molecule cannot touch the metal, or the molecule cannot touch the metal. That can avoid the catalyst effect, or the background, those issues. But the electric field can also transmit to the graphene and to the molecule, and get the enhancement Raman signal. Here is the result we got. Like, if there is no graphene, no metal, the signal is very small. And if we have GERS, we have some signal. And if we have metal and GERS, then we have much stronger signal. Actually, we found the signal is even much stronger than a little bit much stronger than the system without graphene. I mean the conventional SERS system. So the conclusion, I won't go to the details because of the time, but the conclusion is like the GERS can keep most of the advantages from SERS and the GERS, but it have even stronger enhancement than the SERS. Here in some other works, they also construct some other structures like towers and nanoparticles metal nanoparticles with graphene, and they found it has more advantages than the system without graphene. So in the end, we developed a GERS tape for the practical application. The GERS tape includes 3 parts. One is the supporting layer on the bottom. The supporting layer is normally the polymer, transparent polymer without strong Raman signals. And in the middle is the metal nano islands to offer the EM enhancement. And on the top is the molecule, or is the monomer, is graphene. So if we contact the tape with any surface you want, then you can separate the metal and your surface with graphene. Then you can, because it also is flexible and transparent, so you can contact it with any kind of surface. Like we can float it on a solution, so we can get the chemicals signal, the signal from the chemicals in the solution, and we can contact it on the flat surface, and you can get the signal, and you can even contact it with your food, your real food, like cauliflower and any rough surface, you can get strong signals. Yeah. So in the end, let's go to the summary. So in the talk, we introduced the surface enhancement scattering and the graphene enhanced Raman scattering. So both of them are very promising in the microspaces detection. For the GERS, it has strong enhancement factor, but it has some other small issues, like it had to be repeat and quantified. But for GERS, even the enhancement factor is smaller, but it has lots of advantages for us to study the mechanism, to study the chemical mechanism, to get very low noisy and the clean spectrum, and it can give us repeatable and quantitative Raman signal. And close to the practical application, we developed the GERS system where we combine graphene with the metal, and we can get both of the advantages from the two systems. Yeah, so we did some practical applications based on the GERS tape we developed. Yeah, that's all the talk. So in the end, I would like to thank my advisors and the cooperators again. Thank you for attention. And I would like to take any questions.
We have time for some questions. There we have.
What's the enhancement factor for EN for long-term EN?
Oh yeah, it's also.
Did you get the question?
So the question is, what's the enhancement factor for HBN? So if we look at the spectrum, the BN has stronger, here, maybe here. So HBN has weaker enhancement than graphene. We calculated it because it depends on the vibration modes. For the strongest one, you can also get like several tens. Yeah.
Are there any situations where BN is better?
If you say the enhancement factor, graphene is better than HBN, but I mentioned like HBN doesn't have strong dependence on the thickness. Even though you use very thick HBN, you can get stronger signal because HBN is transparent in the visible range light. So that's one of the advantages of HBN, and it's not. It also has very stronger, very significant enhancement, even though it's not as large as graphene. I think that's the situation for HBN.
The thickness dependence, you mean the thickness of EN or thickness of molecule?
Oh, thickness of BN. Sorry. Yes, thickness of BN.
Anything about the molecules? Turn it around. presume for